Hey guys, I was going to do one of these integration by recognition questions. Hope it helps. Okay, so typically with questions like this we need to differentiate something and use that result to work out something else. Now the something else is something we normally would not be able to anti-differentiate. So we do need this technique. So let's get this show on the road. Let that be equal to u, let that be equal to v. So if I want to find out what y dash is equal to, I know it's equal to u v dash plus v u dash, and so that's going to be equal to x times derivative of sine is going to be cos x plus v, which is sine x, times, oh wait, derivative of x is just going to be 1, so it's just plus sine x. So we know that that's equal to, well, it's x cos x plus sine x. Now what this means is the opposite is actually also true. So the opposite means that if I want to anti-differentiate x cos x plus sine x dx, I know that must be equal to what I started with, and that was my x sine x. So for the purposes of today, we're just going to be working out an antiderivative and not worrying about the plus c. You'll see why in a minute. Okay, the next step is we split this into two separate integrals, x cos x dx plus sine x dx, and that we still know is equal to x sine x. Now the reason why we do this is, well, there's two reasons. One is because our target antiderivative is in fact x cos x. So we've already got it split up into something that we want. And the second reason is we recognize that we actually can work out the antiderivative of sine x fairly easily. So let's go ahead with it. So that's going to stay as x cos x dx plus, now when we anti-differentiate, we remember our little code here, SC minus S. So this tells us when we differentiate, sine becomes positive cos, cos becomes negative sine. So it also tells us when we go in the opposite direction, if we've got a negative sine and we're anti-differing, it becomes positive cos. So it changes the sign. So the case here is that we start with a plus sine x, so when we anti-differentiate it, it becomes minus cos x equals x sine x. Now what we're going to do is to collect all of our like terms together, or just get the x cos x on its own, equals x sine x plus cos x. Now we come to the reason why we didn't do the plus c, and that is because, as you probably realize, we've got the 0 and the pi on 4 up here, and this means that we're just going to have to substitute that in. So that means around here we're going to put 0 and pi on 4. So in the first one we get pi on 4 times sine of pi on 4 plus cos pi on 4 minus, well, that's 0 times sine of 0. Well, that was going to be 0 anyway, wasn't it? Because 0 times anything is 0. Plus cos 0. Here we need to exercise a little bit of caution because cos 0 is actually equal to 1. Come back to that later. So now we've got pi on 4 times sine of pi on 4. We need to remember that sine pi on 4 is equal to 1 on root 2 or root 2 on 2 plus cos of pi on 4, which is also root 2 on 2, minus, remember our lonely little 1 over here, so it's minus 1. And so what we can now do is we can say, oh look, I guess there's a common factor here of pi. No, there's not. There's a common factor of root 2 on 2 outside of pi on 4 plus 1, and then we've got the minus 1 at the end. And that, my friends, is it.